There is a line on the mountainside above Lituya Bay, and for a long time it was the only thing at that site anyone could actually measure. It runs across the shoulder of rock that separates Gilbert Inlet from the main body of the bay, on the outer coast of southeast Alaska, roughly 120 miles west of Juneau. Above the line, forest. Below it, at first, almost nothing. Bare rock in places. Soil peeled off, stumps snapped at ground level, and a fringe of shattered trunks lying down in one direction, the way grass lies flat after floodwater crosses a field. The boundary between those two conditions is sharp enough to put a survey instrument on, and a geologist named Don Miller did exactly that. The number he came back with was 1,720 feet above sea level. Nothing in that number describes a mountain. It describes how high water climbed that slope on the night of July 9, 1958. Miller worked for the United States Geological Survey, and he happened to be in Alaska when it happened. He flew into the bay the next day and started measuring. The report he eventually published in 1960 carries a plain title, Giant Waves in Lituya Bay, Alaska, and inside it is one of the strangest sets of field numbers in American geology. He established the elevation of the trim line in section after section around the bay. He counted growth rings on trees at the edge of the damage to work out when older, lower lines had been cut. He mapped where the debris went. And he did all of it on a shoreline where a fishing boat and the two people aboard it had vanished about 18 hours earlier. The way a line like that gets made is not complicated, and that is part of what makes it unsettling. Water has to arrive at that elevation and then leave, fast enough to snap mature Sitka spruce and western hemlock off at the base, high enough that the topmost trees taken out were growing more than a quarter of a mile above the tide. And it has to be a single event, because the boundary is clean. There is no gradient. There is a forest, and then there is a place where the forest ends, and the two are separated by a distance you could step across. So the first question worth asking about the Alaska Panhandle is, what kind of place manufactures a mark like that, and what else that place is holding at the moment? Start with the bay itself, because the shape of it matters more than anything else about the story. Lituya Bay is a T. The stem runs about 7 miles inland from the Gulf of Alaska, and at the head it splits into two arms, Gilbert Inlet to the north and Creon Inlet to the south, set almost in a straight line with each other. Trace that on a chart with no other information, and it looks like an accident of erosion. It isn't. That straight line at the head of the bay is a fault trace. The Fairweather Fault runs directly through it, and the two inlets are what happens when a glacier follows the crushed rock along a fault and hollows it out. The rest of the bay's geometry does the work of a laboratory apparatus. It is deep, over 700 feet through the main basin, with steep walls that go almost straight down. It is narrow, so a wave has nowhere to spread, and the outlet to the ocean is a bottleneck, a gap only a few hundred yards wide with a shallow sill across it, which means that whatever gets started inside the bay stays inside the bay for a while, bouncing between walls that will not let it dissipate. The Tlingit name for it is Ltu.aa, usually translated as the lake within the point, which describes the geography precisely. It is a body of water that behaves like a lake and connects to an ocean through a keyhole. On the night of July 9, 1958, at about 10:15 local time, the Fairweather Fault let go. The magnitude is usually given as 7.8, and estimates in the literature run a bit above and below that. The rupture was long, on the order of a couple of hundred miles along the fault trace, and where the ground could be examined afterward, the southwest side had slid horizontally past the northeast side by something like 20 feet. Geologists call that strike-slip motion. The two blocks of crust scraped past each other sideways. 20 feet of horizontal offset does not make a wave. What it did was shake a mountainside above Gilbert Inlet hard enough to take it down. The slide came off the northeast wall from an elevation of roughly 3,000 feet. estimates put it at about 40 million cubic yards of rock, something like 30 million cubic meters. Numbers at that scale stop meaning much, so here is a way to hold it. A mass of rock that would bury a decent-sized town to the rooftops, released as a single unit, falling most of half a mile into water that was already deep. It landed in the narrow, closed end of a fjord. What happened next is still argued about at the level of physics, and the arguments are interesting in themselves. Scale models built later suggested the initial disturbance in Gilbert Inlet was on the order of 150 meters high, close to 500 feet, before it even started to move down the bay. Miller's own reading of the evidence changed while he was on site. He arrived thinking the earthquake itself had thrown the water around. Then he saw the size of the scar on the wall of the inlet and stopped thinking that. The water went up the opposite slope. That is the mark. 1,720 feet on the spur between Gilbert Inlet and the main bay, which is the highest run-up ever documented anywhere from any wave, by a wide margin. Then it came back down and moved out through the length of Lituya Bay as a wave that stripped the shoreline on both sides to a height of about 700 feet in the upper bay, and less as it traveled, until it reached the entrance and went out into the Gulf of Alaska and stopped being extraordinary. 3 fishing boats were anchored in the bay that night. The Edry was near the south shore, close to the mouth. Howard Ulrich was aboard with his 7-year-old son. He heard the noise from the head of the bay first, which is a detail that keeps showing up in accounts of large slope failures. People hear them before they understand them. Ulrich got the engine going, could not get the anchor up, and let the chain run out to its full length as the wave came down the bay. He described a wall of water. The chain snapped. The Edry rode up the face, over the crest, and back down the other side, and Ulrich took his boat out through the entrance later that night with both of them alive. The Badger, with Bill and Vivian Swanson aboard, was carried stern first across La Chaussee Spit, the low gravel bar that closes off most of the bay's mouth. Swanson said afterward that they were riding just below the crest, like a surfboard, and that they were looking down at trees on the spit as they went over. The boat came apart on the far side. The 2 of them got into a small skiff and were picked up by another vessel. The Sunmore, with Orville and Mickey Wagner aboard, was near the entrance. It was never found. The night's toll is usually put at 5. 2 of those were the Wagners. The others died elsewhere along the coast during the shaking itself, on ground that gave way while they were standing on it. Here is where the case starts to change shape, and it changes because of the growth rings. While Miller was working the shoreline, he noticed that the 1958 trim line was not the only one. There were older boundaries in the forest, lower down, marked by stands of trees that were all the same age because they had all started growing at the same moment, on ground that something had cleared. Count the rings. Allow for the time it takes a spruce seedling to establish itself on scoured ground, and you get a date. He found at least 4 earlier events, one around 1853 or 1854, which had run up to about 400 feet, one in the 1870s, one in 1899, which reached roughly 200, and one in 1936, which had gone to about 490 feet, and which people had actually witnessed. 3 men in a boat lived through the 1936 wave and reported it, and nobody outside the immediate area paid much attention, because a wave in an empty fjord in southeast Alaska in 1936 was not news. So this bay had done a version of the same thing at least 5 times in about a century. That reframes the trim line. A single freak event is a curiosity. A repeating one is a mechanism. And a mechanism has inputs you can go looking for. In this case, there are 3, and each of them turns out to be a property of the whole Panhandle. The first is the fault, which is not just present here but unusually fast. The second is the ice, which has been carving these walls over steep for a very long time, and then walking away from them. The third is water deep enough, and confined enough that a landslide has somewhere to put its energy. Those three conditions occur together along hundreds of miles of this coast. And there is a fourth thing, which is older than all the survey data and easy to skip past. Lituya Bay has a reputation in Tlingit oral tradition, and it is not a vague one. The bay is described as being held by a being who lives at the entrance and who shakes the water, drowning people who come through carelessly. In collections of Northwest Coast material, there is a Tlingit pipe gathered by the ethnographer George Thornton Emmons in the late 1800s, worked with two raised ridges that represent waves closing over a canoe and the people in it. That is a physical object in a museum collection made by people who lived on this coast, depicting the specific hazard of this specific place, well before any of it was measured. The European record backs into the same fact from the other side. In July of 1786, the French expedition under La Pérouse anchored in this bay and named it Port des Français. He sent 2 longboats to sound the entrance channel. The current caught them, both boats capsized in the passage, and 21 men drowned in a matter of minutes. La Pérouse put up a marker on the island in the middle of the bay and named the island Cenotaph, which means an empty tomb. And in the course of talking with the Tlingit who were living there, he wrote down something that most retellings leave out. He was told that 7 large canoes had recently been lost in that same passage, and that one had escaped. The people who lived at Leltu-Daa knew what the entrance did. They knew what the bay did. They had a way of saying it that carried the warning across generations without a tide table. The title of this case says that not even locals talk about what is hiding in the Panhandle, and that framing is worth taking apart right now before the evidence piles up any higher, because the truth is more interesting than the tease. People in Southeast Alaska talk about this coast constantly. They name it in Lingit and in Sadkeel and in English, and the names frequently encode the hazard. What they mostly do not do is talk in the units this story is going to use, because those units live in survey reports, cave inventories, tide gauge records, satellite radar time series, and fault maps. That material is public. It is also scattered across agencies, journals, and archives in a way that means almost nobody, resident or otherwise, has ever seen it assembled in one place. The gap is one of distribution. The material exists. It has simply never been gathered into a single account. So the job here is to assemble it, cluster by cluster, and see how far down the unknown can be pushed before it stops moving. The Fairweather Fault does not stop at Lituya Bay. It is the northern end of something much longer. Offshore, running south past Baranof Island, past Prince of Wales Island, past Haida Gwaii, and down toward Vancouver Island, there is a single continuous fracture in the crust called the Queen Charlotte Fault. Where it comes ashore in Alaska, it takes the name Fairweather. Together, the two are one plate boundary. On the west side, the Pacific Plate. On the east side, North America. The Pacific side is sliding northwest, and it has been doing that for tens of millions of years. And the line where the two grind past each other runs almost exactly along the outer edge of the Alaska Panhandle. That single fact organizes the whole region. The Panhandle is a narrow strip because a plate boundary is holding it to a narrow strip. Now, the number that makes this fault unusual. Satellite geodesy, which measures where the ground actually is from year to year, puts something on the order of 35 to 46 millimeters a year of sideways motion on the Fairweather. Studies that measure offset streams and ridges and moraines on the ground, and then date them, come back with rates at or above 49 millimeters a year, work offshore on the submarine section using seafloor features, whose ages are known from the end of the last glaciation, produced a rate of roughly 50 to 57 millimeters a year, sustained over the last 12 to 17,000 years, and the authors of that study described it as the fastest rate known anywhere on Earth for a strike-slip fault that separates a continent from an ocean basin. Put in units, a person can hold about 2 inches a year. 2 inches sounds negligible. It is a little more than the width of a credit card sideways, every 12 months. Over one human lifetime, that is roughly a dozen feet of accumulated displacement. Over 10,000 years, which is close to the age of the oldest human remains anyone has found on this coast, it is about a third of a mile. Over 1,000,000 years, which is a short interval geologically, it is 30 miles or so. Rock does not slide smoothly at that pace. It sticks, holds strain like a bent spring, and releases in jumps. The jumps are earthquakes, and on a fault this fast they arrive often. Here is the century-scale record on the Queen Charlotte and Fairweather system. 1949, a magnitude 8.1 off Haida Gwaii, still the largest earthquake recorded in Canada since the 1700s. The rupture ran more than 300 miles along the fault. 1958, the Lituya Bay event, magnitude about 7.8, with the surface break traceable for well over 100 miles. 1972, a magnitude 7.6 on the segment offshore of Sitka. It shook the town hard and generated only a small wave, which is worth noting because it shows that a big strike-slip earthquake on this coast does not automatically produce a big tsunami. The water moves when something falls into it. 2012, a magnitude 7.8 at Haida Gwaii on the southern end. 2013, a magnitude 7.5 off Craig in the southern Panhandle. Counting everything of magnitude 7 or greater, this system has produced at least 7 such earthquakes in about 100 years. This is a working plate boundary, running the length of the region, most of it underwater, most of it within 60 miles of towns. The Sitka earthquake of 1972 got a careful re-examination decades later, and the result is one of my favorite pieces of bookkeeping in the whole subject. Researchers tried to account for where the stress that broke that segment came from. About 95% of it, they concluded, came from steady loading from below, the deep part of the fault creeping along at roughly 2 inches a year since about 1848, dragging the shallow, locked part with it. Around 1% came from the neighbors, the stress nudged over by the 1949 rupture to the south and the 1958 rupture to the north. That ratio matters. Each segment fills up on its own schedule, mostly on its own clock, and the neighbors contribute a nudge at the margin. If you want to know what a segment is going to do, you mostly need to know how long it has been since it last let go, and how fast it is loading, which raises the obvious question about the stretches that have not let go in living memory. That question is real, it is asked in the literature, and it does not have a clean answer, because the fault is offshore, and the historical record here is short. Southeast Alaska has been instrumented for seismology for a few decades. It has been written about in any European language for a bit more than 2 centuries. A fault that produces a great earthquake every few hundred years on a given segment is barely sampled by a record that thin. Then there is what happened in 1899, about 180 miles up the coast from Lituya Bay, at Yakutat Bay. In September of that year, a series of severe earthquakes hit the Yakutat area. The largest, on the 10th, is now estimated at around magnitude 8.2. 6 years later, in 1905, 2 geologists named Ralph Tarr and Lawrence Martin went in to measure what it had done, and what they found is still the record holder. Along the shores of Disenchantment Bay, the land had been lifted straight out of the sea. They could measure it precisely because the ocean leaves a mark. Barnacles, mussels, seaweed, all of which grow in a tight band tied to tide level. That band was now stranded in the air, dead and dry, with a new living band established below it. The vertical distance between the old line and the new one is the uplift. The maximum they measured was 47 feet and 4 inches. That is the largest sudden uplift ever measured anywhere on Earth from an earthquake. Not gradual. Not over a century. In one afternoon, a piece of the Alaska coast rose 47 feet. and shellfish that had been underwater at high tide that morning were sitting in the open air by evening. More than 4 stories above the water they came from. In other places along the same shoreline, the ground went the other way and sank. I keep coming back to Taryn Martin's method because it says something about how much of this region's evidence works. Nobody was standing there with an instrument in 1899. The measurement was possible because a natural recorder was running the entire time. Barnacles do not care whether anyone is watching. That is a theme that repeats along this coast. Most of what we know here got recorded by something that was not trying to record anything. Now for the shape of the land, because the fault explains that too. The Panhandle runs roughly 500 miles from the Yakutat area in the north to the border below Ketchikan in the south. And at its narrowest, it is only about 35 miles from salt water to the international boundary. Offshore of the mainland strip sits the Alexander Archipelago, about 1,100 named islands strung out over 300 miles. Those islands are the tops of coastal mountains, with the valleys between them flooded. The channels of the Inside Passage are drowned glacial troughs, and a striking number of them run dead straight for tens of miles, because the ice followed the crushed rock along faults, and faults tend to be straight. When people say the Inside Passage looks engineered, that is what they are responding to. The geometry is structural, and it is worth coming back to, because the pattern runs through the entire map. The vertical dimension is even more extreme than the map suggests. Mount Fairweather, the peak the fault is named for, stands a little over 15,300 feet, and it is roughly a dozen miles from open ocean. There are very few places on the planet where you can go from tidewater to 15,000 feet in that distance. The reason is that the plate boundary here does not slide cleanly. Along one long bend, the motion is not purely sideways. There is a component of convergence, something like 20 millimeters a year of the Pacific side being driven into the continent, and the crust responds by stacking up. The southern, St. Elias and Fairweather ranges are what that stacking looks like. So assemble the ingredients that produce the trim line. A plate boundary moving about 2 inches a year, close enough to the coast that its earthquakes are local. Mountains built by that boundary, rising thousands of feet directly out of deep water. Fjords carved along fault lines, which means the fjord walls are made of rock that has already been shattered once, and enough shaking, often enough to test all of it regularly. Lituya Bay is the case where somebody happened to be present, and where the geometry concentrated the results so extravagantly that the number became famous. The system that made it runs the length of this coast. That is the first cluster of evidence, and it answers part of the question. The Panhandle is physically capable of moving enormous amounts of rock into confined deep water on short notice, and the mechanism that does it is running continuously and is well characterized. The next question is narrower, and it turns out to be the one that keeps mattering. How often does the coast do this without an earthquake to trigger it? And what has been loosening the slopes in the meantime? The answer to that starts with ice. One more thing about the fault, because it explains something you can see from an airplane window. Along much of its onshore length, the Fairweather Fault is a landform you could walk. It runs as a straight linear trench through the mountains. And where it crosses ridges and valleys, it leaves the ground offset. A stream comes down a slope, crosses the fault, and then jogs sideways before continuing. A moraine dropped by a glacier gets cut in half and the halves pulled apart. A ridge crest steps. Geologists have spent years walking that trace and measuring those offsets, and the technique is straightforward in principle. Find a feature you can date, measure your estuary, measure how far the fault has displaced it, divide one by the other. Do that at enough sites, and you have a slip rate that is independent of satellites and independent of the earthquake catalog. That work has produced something else. In the landforms along the trace, there is evidence of ruptures that came before 1958. Older offsets, older scarps, at scales that indicate large earthquakes on the same segment in the past, well before anybody in the area was writing anything down. That is what paleoseismology is for. The written record on this coast is roughly 2 centuries deep, and the instrumental record is a few decades. The ground itself keeps a longer one, and the only way to read it is to go out and dig into it. The same structural grain shows up all over the map of Southeast Alaska once you know to look for it. Chatham Strait is the most obvious case. It runs north to south for well over 100 miles between Admiralty Island on one side and Chichagof and Baranof on the other, and on a chart it is almost unnervingly straight. That is because it follows a major fault of its own, one linked to the Great Fault System that runs across interior Alaska. Ice found the shattered rock along the fault, excavated it preferentially, and left a trench that filled with seawater when the ice went. Lynn Canal continues the same trend to the north, which is why the route to the Klondike ran up a fjord that is essentially a fault line with a ferry route in it. The long parallel channels of the Inside Passage follow a structural fabric, and the fabric is a great deal older than the water sitting in it, which is why the Panhandle looks, on a map, like something that was cut. The straight lines are real, they are ancient, and they were there waiting before the ice arrived to exploit them. In 1794, George Vancouver's expedition worked its way along the north shore of Icy Strait, in the top corner of what is now southeast Alaska. Where a large bay opens today, his crews found a wall of ice. There was an indentation, a few miles deep, and then the ice, several thousand feet thick, filling everything behind it and running back into the mountains. 85 years later, in 1879, John Muir came to the same place and found that the ice front had gone back roughly 48 miles. He was looking up a bay that had not existed when Vancouver passed. By 1916, the Grand Pacific Glacier had pulled back to the head of Tar Inlet, about 65 miles from the mouth. That is Glacier Bay. It is generally described as the fastest, well-documented glacial retreat anywhere in the historical record. And the thing that makes it usable as evidence is that people wrote down where the ice was at intervals across 2 centuries. The people who lost the most in that sequence recorded it first, and what they recorded was the advance. The bay is Hoona Tlingit homeland. The Hoona name for the area is Se-Shu-Yi, which is usually given as at the edge of the glacial silt. And the clans lived along the valley floor there, in villages and fish camps, for a very long time. In the 1750s, at the peak of the cold interval Europeans call the Little Ice Age, the glacier came forward. Tlingit oral history describes it moving faster than a dog could run. It destroyed the villages, filled the valley, and only stopped when it hit the salt water of Icy Strait. The clans left by canoe. They resettled at Sunaya, on Chichagof Island across the strait, the town now called Hoona, and the name Shunaya is usually translated as protection from the north wind. Geologists went and checked. The moraines, the buried forests, the dated wood in the till, all of it lines up with an advance culminating in the middle 1700s. The oral account of that advance is one of the more frequently cited cases anywhere of indigenous historical tradition, matching a physical record in detail. And it is worth being specific about what matched: the timing, the direction, the fact that the ice reached tidewater, and the fact that it happened fast enough for people to have to run. 260 years later, on the 25th of August, 2016, the Hoona Tlingit opened a clan house at Bartlett Cove, inside Glacier Bay National Park, the first permanent Hoona structure in the homeland in over 2 centuries. It is called Junaa Shuka Heat, the Hoona Ancestors' House. It carries the crests of the 4 Glacier Bay clans, the Chukanadi, the Kagwantan, the Wushkitan, and the Takdaintan. More than 800 people came. 3 hand-carved dugout canoes came in out of the fog at the cove. That is the human timeline of this ice. Now the physical one, which turns out to be doing something to the entire northern panhandle right now. When you put a mile of ice on the crust goes down. The mantle underneath behaves, over long periods, like an extremely stiff fluid, and it flows sideways out from under the load. Take the load off, and the process reverses. The crust comes back up partly instantly and elastically, partly slowly, as mantle material creeps back in underneath. Southeast Alaska took a very large load off in a very short time. The result is one of the fastest rates of land uplift measured anywhere on the planet. Around Upper Glacier Bay, where the ice loss since the 1750s has been greatest, the ground is rising at something like 30 millimeters a year, about 1 1/5 inches. Around Juneau, the modeled figure is roughly 15 millimeters a year, call it a bit over half an inch. Those rates are measured with permanent satellite positioning stations that sit on bedrock and report where they are, continuously, for years at a time. Half an inch sounds like nothing. Run it out. Over a decade, it is 5 inches. Over the average American mortgage, it is more than a foot. Over a lifetime in Juneau, it is close to 4 feet of vertical change in the relationship between the land and the sea. And along the flat, gently sloping tidal margins, where most of the town's usable ground is, a foot of vertical change moves the waterline a very long way sideways. That produces consequences that are strange to describe because they run backwards from everything else being reported about coastlines. Sea level worldwide is going up. In the northern Panhandle, relative sea level is going down, and going down fast, because the land is winning the race. So the shoreline is retreating seaward. Tidal flats are becoming meadows. Meadows are becoming shrub. Boat ramps that used to reach water at half tide reach mud instead. Small harbors need dredging that they did not need. Channels that were charted a few decades ago carry less water than the chart says. And then there is the legal part, which is where the geology becomes almost comic. When ground that used to be tidal rises permanently above the high tide line, it stops being state-owned tideland and starts being new upland. Alaska law provides a process. The adjacent property owner can go to court, quiet the title, and add the new ground to their parcel. In the Juneau area, this has been happening steadily. One landowner has nearly tripled the acreage of the original parcel through accreted land, with the potential, if the process continues, to increase it many times over. Land is being manufactured, continuously, by the absence of a glacier. Somebody's property line is moving because of a mass of ice that started melting before the Civil War. There is a cost attached, and the Mendenhall Wetlands State Game Refuge is where it shows. That refuge is estuary, the productive tidal zone at the mouth of the Mendenhall River, and it depends on being tidal. Uplift is converting it, acre by acre, into dry ground. The refuge is losing exactly the habitat it was created to protect, and nothing is being done wrong by anybody. The ground is simply coming up. The same glacier that is manufacturing real estate is also in August trying to remove some. Above the Mendenhall Glacier, there is a side valley called Suicide Basin. A tributary glacier used to fill it. That tributary shrank back and left a bowl. And every summer the bowl fills with meltwater and rain, held in place by the main glacier acting as a dam. At some point each season, the water finds a way underneath the ice, and the basin empties into the lake, and down the Mendenhall River through the middle of a residential valley. This has been happening since about 2011. Then it started escalating. In 2023, the river crested at 14.97 feet, took out riverbank, and dropped houses into the water. In 2024, it went higher, 15.99 feet, and damaged close to 300 homes. In 2025, it broke the record again, 16.65 feet on the 13th of August, and that year the damage was far lower, around 50 homes, because temporary barriers had been installed along the vulnerable stretches in the meantime. 3 consecutive record crests, each one higher than the last in a valley where people live. The mechanism is entirely understood. The size of the next one is not, because it depends on how much water the basin holds and how the dam behaves that particular year. And both of those change as the glacier changes. There is a quieter version of the same story happening in the forest, and it took researchers a while to work out because the explanation runs opposite to intuition. Yellow cedar is one of the most valuable and culturally important trees on this coast. Across a large area of southeast Alaska, it has been dying, in stands where dead trunks stand gray and bare for decades. The obvious guess would be drought or heat. The actual mechanism worked out by Forest Service researchers is freezing. Yellow cedar carries its fine roots very shallow. It comes out of winter dormancy early when late winter weather turns warm. If there is snow on the ground, the roots are insulated and a spring cold snap does nothing. If there is no snow, the roots freeze and the tree is fatally injured. Warmer winters have removed the snow, and the snow was the protection. The mortality follows snow cover far more closely than it follows temperature alone, which is why the decline shows up in low elevation, low snow zones, and stops where the snowpack still holds through spring. Estimates put the affected area in southeast Alaska at roughly 500,000 acres, with a larger figure of around 600,000 acres when British Columbia is included, and mortality inside affected stands running very high. A tree species is being killed by warmth, through the specific mechanism of cold. It is the kind of result that makes me trust the people who worked it out, because nobody would invent it. Along the water, the ice does something more immediate. Southeast Alaska still has active tidewater glaciers, ice that reaches salt water and calves directly into it. Marjorie and Johns Hopkins in Glacier Bay, Dawes in Endicott Arm, the two Sawyers at the head of Tracy Arm, and LeConte at the head of a narrow fjord about 25 miles east of Petersburg, which is the southernmost tidewater glacier in the northern hemisphere. Its Tlingit name is Zeidel Set. Petersburg exists partly because of it, because before mechanical refrigeration, a town that could send a boat up the fjord and come back with ice had a way to keep fish. A tidewater face is an unstable structure that is constantly failing. Most of the failures are small and loud and go into the water at the front. The dangerous kind happens below the surface. A block detaches underwater, and because ice floats, it comes up. Fast. It can surface hundreds of feet from the ice front, in water that looked empty a second earlier. In the trade, they are called shooters, and they are the reason experienced operators keep their distance from a glacier face, even when the face is quiet, and the reason certain inlets are treated with real caution. The wave that comes off a large calving event is a genuine hazard to small vessels. In August of 2011, in Tracy Arm, a 65-foot tour boat took a calving wave, and a passenger broke her leg. There are near misses on video every summer. That is a nuisance-scale version of the mechanism from Lituya Bay. Something solid arrives suddenly in a confined body of deep water. The full-scale version arrived in that same fjord 14 years later, at 5:30 in the morning, in a place where, by pure chance, nothing happened to be floating. Glacier Bay is worth staying with because of who ended up in charge of it and how long it took to sort that out. In 1916, an ecologist named William Skinner Cooper came up the bay and realized what he was standing in. The ice had withdrawn from the mouth first and the head last, which meant that as you travel up the bay, you pass across ground that was uncovered at known and progressively later dates. Bare rock at one end, moss and dryas, alder thickets, willow, young spruce, mature spruce and hemlock forest at the other, roughly 200 years of ecological succession laid out along 60 miles of shoreline, with the dates already established by the historical record of where the ice front stood. There is almost nowhere else on Earth where that experiment is set up for you. Cooper established permanent study plots and then went to the Ecological Society of America and argued that the place needed protection so the plots would survive. That advocacy is why, in 1925, Glacier Bay was proclaimed a national monument. It became a national park and preserve in 1980 under the Alaska Lands Act. Cooper's plots have been revisited for over a century now, which makes them one of the longest continuously monitored ecological experiments anywhere. So a piece of Hunatlingit homeland became a federal monument because an ecologist wanted his quadrats left alone. That sentence contains the whole problem, and the Huna have spent the century since working on it. When land becomes a national park, the uses permitted on it change. The Hunatlingit had been coming back into Glacier Bay as the ice withdrew, taking fish, seal, berries, and, among other things, the eggs of glaucous-winged gulls, which is a traditional spring harvest with real cultural weight. Park status and federal wildlife law between them made that harvest illegal. Getting it back took roughly 25 years, and every level of the American system. A change to the Migratory Bird Treaty Protocols in 1995 opened the door to Alaska. Native subsistence egg gathering in principle. The National Park Service then ran a full environmental impact study completed around 2010, which concluded that a controlled harvest could be sustainable. Biologists monitored candidate gull colonies for several years. Congress passed a specific act signed in July of 2014, authorizing the Huna Indian Association to gather gull eggs in Glacier Bay twice a year at up to 5 locations. In May of 2015, 4 members of the association carried out an experimental research harvest of about 100 eggs from 2 colonies, and the eggs were distributed to elders. The Park Service completed the regulatory implementation in 2019. The first regular harvest under the new arrangement took place on the 1st of June, 2020. An environmental impact statement, an act of Congress, and a research harvest, so that people could gather eggs in their own homeland. I am not going to pretend I find that a neutral piece of administrative history, but the outcome is worth being clear about, because it is the same outcome as the cave. The knowledge got better, and the authority ended up in the right hands, slowly, through a process that everybody involved found exhausting. And the science that came out of Glacier Bay is substantial. The uplift measurements that showed how fast the land is rising came from here. The Tidewater Glacier work, the whale research, the succession plots, the sediment cores that record the ice advances of the past several thousand years. It is one of the most intensively studied pieces of coastline in Alaska, which is exactly what makes the rest of the Panhandle look so thinly covered by comparison. Glacier Bay National Park and Preserve covers a little over 3.2 million acres. The region around it runs to tens of millions. Most of that has never had a permanent plot, a monitoring station, or a repeat survey of any kind on it. Tracy Arm is a fjord about 80 miles south of Juneau. It is narrow, steep-walled, roughly 30 miles long, and in summer it is one of the busiest pieces of water in southeast Alaska. Cruise ships go up it. Day boats out of Juneau go up it. Kayakers get dropped at the islands near the head. At the far end are the 2 Sawyer glaciers, and the whole point of the trip is to get close to the ice. On the 10th of August, 2025, at 26 minutes past 5 in the morning, a mountainside above the terminus of South Sawyer Glacier came off. The volume estimates run up to around 100 million cubic meters for the total failure, with something on the order of 64 million cubic meters going into the water. That is roughly twice the mass that fell into Gilbert Inlet in 1958. The wave ran up the opposite wall of the fjord to 481 meters, about 1,580 feet. That is the second highest tsunami run-up ever measured anywhere on Earth. The only one above it is the trim line at Lituya Bay. Near Sawyer Island, further down the fjord, the wave was still at least 30 meters, close to 100 feet. It kept going. 80 miles away, the tide gauge at Juneau registered 36 centimeters, about 14 inches, arriving as a clean signal from a landslide in a side fjord. Nobody was hurt. Kayakers camped on Harbor Island lost gear that was swept off the beach. The reason the death toll was 0 is that it happened at 26 past 5 in the morning in the second week of August, before the day's traffic had come up the arm. It would be easy to turn that into melodrama, and the physics does not need the help. Here is the defensible version. The mechanism that made the most famous wave in the world in 1958 repeated itself 67 years later, at nearly the same scale, in a fjord that carries thousands of passengers on a typical summer day. And the interval between the event and the first vessels of the morning was a matter of hours. And this one had no earthquake. That is the part that changes the shape of the case. Lituya Bay had a magnitude 7.8 to shake the slope loose. Tracy Arm in 2025 did not. The slope failed on its own. What had changed above that slope was the ice. South Sawyer Glacier has pulled back well over half a mile from its mapped position. When a glacier fills a valley, it presses against the valley walls and holds them. Take the ice away, and the wall is left standing at an angle it was never stable at without support, with fresh fractures, with meltwater getting into those fractures, and with permafrost in the high rock warming. Researchers call the loss of that support debuttressing, which is an ugly word for a simple idea. The ice was a retaining wall. It is being removed. So the ice comes back into this story in a completely different role. In the first cluster, it was the thing that carved the fjords. Then it was the thing whose removal is lifting the land and rewriting property lines. Now it is the thing whose removal is releasing mountainsides into deep water on a coast where deep water is everywhere. That reframes every steep slope above every fjord in the northern Panhandle as an open question. The question has a smaller, more frequent, and much deadlier version, and it does not involve fjords at all. It involves rain. On the morning of the 18th of August, 2015, a storm sat on Sitka. Between midnight and 10 in the morning, 2.6 inches of rain fell, and 1.5 inches of that came inside a single 3-hour window. Around 60 landslides came off the slopes in and around the town that day. Most did no harm. One of them started on Harbor Mountain, above a new subdivision on the edge of town, and ran about 1,200 feet down into a house, under construction on South Kramer Avenue. 3 people died. Elmer Diaz, who was 26, his brother Ulysses, who was 25, and William Stortz, 62, who was the city's building official and who had gone up that morning to look at the road conditions. Sitka is a town of about 8,000 people on the outer coast of Baranof Island. It has mountains behind it, an ocean in front of it, and, like almost every community in this region, it is built on the narrow bench in between, because that is the only ground there is. What Sitka did next is the reason this case is worth telling in detail. The town did not relocate, which would have been impossible, and did not simply absorb the loss. It went and got the measurement. The Sitka Sound Science Center, working with the Sitka Tribe of Alaska, brought in researchers from the University of Oregon, the United States Geological Survey, and the National Weather Service office in Juneau, plus a team from the Rand Corporation whose job was the part nobody usually funds, figuring out how to tell people about risk in a way that actually changes what they do. The National Science Foundation put in around $2.1 million. The technical problem they hit is the interesting one, and it is a problem that applies to almost everything in this region. To predict landslides from rainfall, you need a record of rainstorms that produced landslides and rainstorms that did not. The team assembled everything available for Sitka from November of 2002 to December of 2020. Across that 18-year window, they had more than 6,000 days with recorded precipitation, and exactly 5 days that produced landslides they could tie to a specific rainfall event. 5. In 18 years. They ran 136 different statistical models against that. And what came out is now published and is running as a public dashboard, and it uses one variable: the maximum rainfall accumulated in any 3-hour window. 21.3 millimeters in 3 hours, which is 0.84 inches, takes the town to a medium hazard level. At that intensity, the estimated probability of a landslide somewhere in the area is around 1%. 34 millimeters in 3 hours, 1.34 inches, takes it to high. At that intensity, the estimated probability jumps to roughly 70%. Go back to the morning of the 18th of August, 2015. 1.5 inches in 3 hours, above the high threshold, before anyone had derived a threshold. Now the number that matters most, and it is the one the researchers were most careful about. The landslides in the record for which they had good timing occurred 1 to 3 hours after peak rainfall. 1 to 3 hours. The physical warning interval built into that system is exactly that short. Water has to get into the soil, pressure has to build in the pore spaces, and then the slope goes. The dashboard can push the horizon out further by using weather forecasts, so a resident can see days in advance that a dangerous storm may be coming. But once the rain is actually falling at that intensity, what stands between the trigger and the failure is a couple of hours. One more detail about the dashboard belongs in an honest account. It is run by a nonprofit. The Science Center operates it on forecasts from the National Weather Service and observations from a rain gauge at the airport, and it has stated plainly that it does not currently have grant funding to maintain the thing. A warning system for a town that lost 3 people is being kept alive on soft money. The pattern repeats up and down the coast, and the details get worse as it goes. The 2nd of December, 2020, in Haines, at 17 minutes past 1 in the afternoon. A slope above Beach Road failed and took out houses. 2 people died, and their bodies were never recovered. The rainfall that day, 6.62 inches, broke the all-time daily record at the town's long-running weather station. 2 days together came to about 10.25 inches, which is in the range of a once-in-500 years event for that location. It was an atmospheric river landing on snow, which is the combination the literature flags as the most dangerous of all, because the snow supplies additional water and the ground underneath is already saturated. That one at least came with a warning in the form of a record-breaking storm. The 20th of November, 2023, near Wrangell, did not. At about 9 in the evening, a slope let go above the Zimovia Highway, roughly 11 miles south of town, and crossed the road on a front about 450 feet wide, taking out homes. 6 people died. The storm that produced it dropped a little over 3 inches of rain in 24 hours, with nearly half of that between 3 in the afternoon and 9 at night. When researchers worked out the intensity over the 6 hours before failure, they got something around 5 millimeters an hour, which for Wrangell corresponds to about a 1-year recurrence interval, a 1-year storm. The kind of weather that town gets on average annually. The subsequent analysis of the Wrangell event made a broader observation about the region. Every recent fatal landslide in southeast Alaska has been triggered by an atmospheric river, the long plumes of concentrated water vapor that come in off the Pacific and unload on the first mountains they hit. And the first mountains they hit are these. How well is any of this mapped? The Forest Service inventory for the Tongass, built up over decades from aerial photography and field mapping, contains something on the order of 12 to 15,000 landslides. That sounds thorough until you consider how the record of what those landslides did to people was assembled. In 2024, researchers published a database of news-reported landslide impacts in southeast Alaska from 1990 to 2024. It contains 162 events across 7 population centers, and it was compiled by reading 13 local news outlets. To find out how often landslides had hurt people in this region, somebody had to read the newspapers. And there is one slope that has been watched, by name, for a long time, because of what sits downstream of it. On the north shore of Tidal Inlet, in Glacier Bay, there is a block of mountainside, estimated at 5 to 10 million cubic meters, perched above the water. It moved once already. Comparison of old photographs and field evidence shows it slipped sometime between 1892 and 1919, shortly after the glacier that had been filling Tidal Inlet withdrew in about 1890. Same mechanism as Tracy Arm, a century earlier. It did not go all the way. It is still there, and it is still moving. Global positioning instruments placed on the mass measured it creeping at 3 to 4 centimeters a year. The United States Geological Survey modeled what happens if it does go. Inside Tidal Inlet, waves on the order of 76 meters with run-up around 200 meters on the opposite shore, traveling at 45 to 50 meters per second, which is better than 100 miles an hour, out into the west arm of Glacier Bay, arriving with the greatest amplitude within about 40 minutes and continuing to slosh for hours afterward. The west arm of Glacier Bay is where the large cruise ships go on a schedule all summer. Nothing about that is a secret. It is in the published literature, it has been for 2 decades. And the Park Service is aware of it. It is simply one of the many things about this coast that lives in a technical report and never made the jump into conversation. So the second cluster answers more of the question. The Panhandle can move mountain sides into deep water without an earthquake. It does so more often as the ice withdraws. It kills people on ordinary rainy nights in ordinary towns. And the total instrumental record we have for calibrating any of it amounts to 5 landslide days in 18 years at the one place that has been studied hardest. That is a lot of capability and very little measurement. Now turn the problem around. Everything so far has been about a landscape that moves. What happens where it holds still? That question has an answer, and it is underground. There is a consequence of all this that took me a while to see properly, and once seen, it is difficult to put down. The tsunami warning system that protects the Pacific coast of the United States is built around distant sources. An earthquake happens somewhere. Seismic waves travel through rock at several miles per second, while the water moves at the speed of a jetliner. That difference in speed is the entire warning. The seismic signal arrives, the warning centers evaluate it. Deep ocean pressure sensors confirm that a wave is actually running, and coastal communities get anywhere from tens of minutes to many hours. That architecture does nothing at all for a landslide inside a fjord. When a mountainside falls into Tracy Arm, the opposite wall of the fjord is perhaps half a mile away. The wave that ran 481 meters up that wall in 2025 got there in something on the order of tens of seconds. There is no window in which to notice, evaluate, and communicate. The event and the impact are effectively the same moment. Further down the fjord, there is a bit more time, and it is still measured in minutes. And at Juneau, 80 miles away, what arrived was 14 inches on a tide gauge, which is a scientifically valuable record and no threat to anybody. So the hazard has a peculiar profile. Enormous, within a mile or two of the source. Modest a few miles away. Negligible beyond that. Which means the entire risk is a question of whether anything happens to be near the slope at the moment it goes. And in a region where the scenery is the product, and the boats go to the scenery, the answer in summer is usually yes. That is why the timing at Tracy Arm mattered so much, and why the tide gauge record is worth thinking about. The best instrumental account of the second largest wave run-up ever measured on this planet is a routine harbor water level record, collected for shipping, 80 miles from where it happened. Now the other half of the problem, which belongs to the towns. A community here sits on a narrow bench with mountains rising immediately behind it and deep water immediately in front. It has 2 serious sudden hazards. One arrives from the water. One arrives from the slope. For a tsunami, you go uphill. For a landslide, you get out from under the hill. Researchers working with Sitka on its warning system wrote up the community's situation under exactly that title. Run uphill for a tsunami. Downhill for a landslide. It reads like a paradox, and it is simply a description. The two evacuation directions are opposite, and there are conditions in which both hazards are live at once, since a large earthquake can shake slopes loose while it is also moving water, and a severe atmospheric river can saturate a hillside during the same storm that is pushing a surge into the harbor, which means the practical question for a resident, at the moment it matters, is which hazard this is. That is not a comfortable thing to have to determine quickly, and it is a big part of why the Sitka work puts so much effort into risk communication alongside the physics. There is one more piece of context for the Tracy Arm event that has changed how researchers are looking at this coast. The slope that failed had been supported by ice, and the ice had gone. That mechanism applies everywhere in this region, where a glacier has pulled back from a valley wall above deep water, and in the northern Panhandle that describes an enormous amount of shoreline. The event has pushed attention onto exactly those settings: fjords with recently retreated tidewater glaciers, steep rock walls, and vessel traffic. The uncomfortable part is that identifying which of those slopes is currently moving requires either instruments on the slope or repeated high-resolution surveys of it, and there are a great many slopes. Tidal Inlet was found because somebody compared photographs decades apart, and then went and put positioning instruments on the moving block. That is the level of effort involved, and it has been applied so far to one slope. Before the caves, a word about why the caves are the only place this record survives. The Alaska Panhandle is one of the wettest inhabited places on the planet. At Little Port Walter, a small research station on the outer coast of Baranof Island, the current 30-year normal for annual precipitation is a little over 236 inches, nearly 20 feet of water a year, falling on one spot. In its wettest recorded year, 1987, that station took 292 inches. It came close to that again in 2023. Ketchikan averages around 140 inches. Yakutat around 155 plus better than 140 inches of snow. Juneau, sheltered further inside the channels, gets a comparatively modest 62 inches of liquid, but spreads it across roughly 230 days a year with measurable precipitation, which is a different kind of statistic and a more honest description of what living there is like. Downtown Juneau, incidentally, gets about half again as much rain as the airport 8 miles away, which tells you how local the weather is when mountains are this close together. Now consider what all that water does to evidence. Rain moves through decaying vegetation, picks up organic acids, and arrives in the soil as a mild acid bath. The classic Southeast Alaska ground surface is muskeg, waterlogged and sour. Bone put into that ground does not last. Neither does shell or antler or any of the material archaeologists normally use to date a site. Wood rots, fire hearths get churned, and on top of that chemistry, you have the physical problems already established. Ground that rises, ground that slides, sea level that moves relative to the land, and glaciers that periodically come down and scrape whole valleys clean. If a coastline were designed to erase the record of who lived on it, it would look like this, except for the limestone. On Prince of Wales Island, and on several of the islands around it, there are broad belts of very old limestone and marble, laid down as marine sediment hundreds of millions of years ago, and later hardened and tilted. Limestone has one relevant property. It dissolves in weakly acidic water. And weakly acidic water is precisely what this coast delivers in volume every single year. The result is karst, streams that run along the surface and then vanish into the ground, sinkholes in the forest floor, some big enough to swallow a truck, ridges honeycombed underneath, and caves, thousands of feet of them, dry and cool and stable, and, crucially, chemically the opposite of the ground above. Inside a limestone cave, water percolating through is saturated with dissolved calcium carbonate. Bone that lands on that floor does not dissolve. It gets buried in fine sediment held at a steady cool temperature and preserved. In a region where the surface destroys everything, the caves under the surface keep it. More than 600 caves have been found on Prince of Wales Island. The most accessible one, El Capitan, is the longest mapped cave in Alaska, with something over 13,000 feet of surveyed passage, close to 2.5 miles. There is a wooden staircase up through the forest to the entrance, and the Forest Service runs tours in summer, and it is a good introduction to what the rest of the island is doing underneath. Most of that mapping is recent. In the mid-1990s, the Tongass Cave Project was set up, a joint effort between the Tongass National Forest and the National Speleological Society to survey and protect the karst. Before that, most of it was simply unknown to anyone outside the people who lived there. In 1990, a caver named Kevin Allred pushed into an upper passage in El Capitan and found bones on the floor. He named the passage the hibernaculum, because that is what it had been. The bones turned out to be a great deal older than anyone expected, and that discovery opened up a systematic hunt through the karst that has been running ever since. The paleontologist who did most of the work is Timothy Heaton from the University of South Dakota, and what he pulled out of these caves rewrote the environmental history of the region. Take one cave at Protection Head on the northern tip of Prince of Wales Island, about half a mile inland. It was found in 1993 by Kevin Allred and Mark Fritzke, and it got its name from the posture required to get into it. On Your Knees Cave. Roughly 100 animal bone samples from that cave were radiocarbon dated. The results showed animals using it more or less continuously across the last 40,000 years, a running record 40 millennia long. And the animals in the record are the wrong animals for a rainforest: brown bear and black bear, with dates running back into the 35 to 41,000 year range. Ringed seal, which is a sea ice animal. Arctic fox. It is a fauna you would expect on the northern Alaskan coast, not on a wooded island at the latitude of Scotland. It is direct evidence that this coast, at the height of the last glaciation, was a cold, partly ice-covered marine edge environment, with animals living on and around it. Which leads to the argument, and the argument is still running. If bears were living on these islands before, during, and after the last glacial maximum, then some ice-free ground must have persisted here through the coldest part of the Ice Age. A refuge. That has enormous implications, because a chain of habitable coastal ground would be a plausible route for people moving south from Beringia, along the shore, in boats, while the interior of the continent was still sealed by ice. The counter-argument is equally physical. A study published in 2022 used cosmogenic nuclide dating, which measures how long a rock surface has been exposed to the sky, on bedrock in the Alexander Archipelago. The conclusion was that there were no ice-free refuges here during the peak of the last glaciation, because the surfaces they tested had all been under ice. Those two lines of evidence are hard to reconcile, and specialists are still working on it. That disagreement is worth flagging clearly because it is exactly the kind of thing that gets flattened in retellings. The bare bones are real and dated. The bedrock exposure ages are real and dated. What the combination means is unsettled. Then, in 1996, in the same cave, they found a person, not a burial. Scattered fragments. A piece of lower jaw with teeth, parts of a pelvis, a few other bones, in cave sediment alongside animal remains. Radiocarbon dates on the human material came in between about 9,730 and 9,880 radiocarbon years before present, which converts to somewhere close to 10,300 calendar years ago. At that time, these were the oldest human remains found anywhere on the northwest coast of North America. What the chemistry said about him is the part I find hardest to stop thinking about. Stable isotope analysis measures what a person ate because the ratio of certain isotopes in bone, reflects the ratio in the diet. His signature was almost entirely marine. This was a person who lived on the ocean. Fish, sea mammals, shellfish, essentially no terrestrial protein at all. 10,300 years ago, on this coast, somebody was already fully committed to the sea. The stone tools found with him extend that further. Among them were microblades, small precise flakes struck from a prepared core, and some of the material was obsidian. Obsidian is traceable because every volcanic source has its own chemical fingerprint. The fingerprint on some of the material from that cave points to the Mount Edziza volcanic complex in the interior of British Columbia, hundreds of miles away. So the picture assembles. 10,300 years ago, a person on the outer coast of what is now southeast Alaska, eating almost exclusively from the ocean, carrying tools made of volcanic glass that came from a long way off. That is somebody inside a network, with the network's material in his hands. The genetics closed, part of the loop. His mitochondrial lineage belongs to haplogroup D, which is found down the Pacific coast of the Americas. Later work, using more of his genome, published in 2017, placed him firmly in the ancestry of indigenous populations of the region, with the closest living relationships to Tlingit, Haida, and Tsimshian people. The conclusion is straightforward and was already being asserted by the people it concerned. The ancestors of the people living on this coast today have been here since close to the end of the Ice Age. Now, the part of this that I think is genuinely the most important, because it goes to how a record gets made and who controls it. Human remains from a federally managed forest fall under the Native American Graves Protection and Repatriation Act. The Tlingit tribes of Prince of Wales Island, at Klawok, and at Craig had standing to claim them, and did. What happened next was an arrangement. Tribal representatives, the Forest Service, and the researchers negotiated terms under which the study proceeded, with tribal oversight, for a defined period, on defined questions, with the understanding that the remains would come home at the end. The tribes gave him a name, Shukaka, man ahead of us, a name that places him in a line of descent, with living people at the other end of it. In 2008, he was reburied on Prince of Wales Island, in a location that was not published, in a bentwood box made by a Tlingit master carver, with an inner liner woven by a Tlingit weaver, in a ceremony held by the communities he belonged to. At the time, he was the oldest set of human remains ever repatriated in the United States. Every scientific result described above exists, because that arrangement held. The isotope work, the obsidian sourcing, the genome, all of it was done with permission, and inside a schedule that ended with reburial. The record of the peopling of this coast is more complete, not less, because the tribes were the ones deciding. I said at the start that the notion of a panhandle nobody talks about deserves taking apart. Here is the sharpest version of why. The oldest human evidence on this coast was found by cavers, dated by scientists, named by Tlingit clans, studied by agreement, and buried by the people whose ancestor he is. Every stage of that involved the people who lived there, deciding. The obsidian in his toolkit points somewhere else, though, and it is worth following. Obsidian is volcanic glass. It forms when certain lavas cool too fast to crystallize. The pieces in that cave came from a volcanic field in British Columbia, which means people were carrying material across a long distance. And it also means that a working volcano was part of the world these communities lived in. Which brings up something about the Panhandle that almost nobody outside the region has on their mental map at all. There is a volcano in southeast Alaska. It sits in plain view of a town of 8,000 people. And between 2018 and 2022, it did something that nobody noticed for 3.5 years. Across Sitka Sound from the town of Sitka, on Kruzof Island, about 15 miles west, there is a cone. It is symmetrical, snow-covered most of the year, with a crater at the top, and it rises a little over 3,200 feet straight out of the water, every photograph of Sitka has it in the background. It is on the town's logos, and its signage, and a fair amount of its coffee shop art. Its Tlingit name is Lu Sha. On charts, it is Mount Edgecumbe, named by James Cook's expedition in 1778. It is a volcano. Not a metaphorical one, not an extinct one. An actual volcano with a magma system underneath it, and it belongs to a group of vents on southern Kruzof Island, collectively called the Mount Edgecumbe Volcanic Field. Almost nobody outside Southeast Alaska knows this. When people list American volcanoes, they get the Cascades and the Aleutians and Hawaii. A volcanic cone in the rainforest of the Panhandle, in plain view of a town of about 8,000 people, tends to be filed under scenery. Part of the reason it gets overlooked is that it should not really be there. Volcanoes normally form where one plate dives beneath another, and water driven off the sinking slab makes the overlying mantle melt. It is what builds the Cascades and the Aleutians and most of the Ring of Fire. Southeast Alaska is not that kind of boundary. Here the plates slide past each other sideways. Strike-slip margins are not supposed to be volcanic, but a strike-slip boundary is not a clean cut. Where the fault bends or steps sideways, the crust locally pulls apart, and if it pulls apart enough, decompression lets mantle material melt and find a path up. That is the current understanding of what feeds Edgecumbe. So the fault appears again, in a third role. It built the mountains, it shakes the slopes, and it opened the pathway that put a volcano on this coast. The eruptive record is preserved in two places, in the ground on Kruzof and around Sitka, and in the mud on the sea floor, where ash layers settle and get buried in order, each one a datable horizon. What that record shows is a field that has done something genuinely big. Between roughly 13,000 and 14,500 years ago, at the end of the last glaciation, the Edgecumbe Field produced a series of major explosive eruptions. The volume estimate for the pyroclastic material runs to about 7.5 cubic kilometers of dense rock. The tephra layer from that phase is around a meter thick near Sitka, and in places on Kruzof Island, more than 30 meters thick. Ash from it has been identified as far as Juneau and Lituya Bay, roughly 200 kilometers away in different directions. And there are pyroclastic flow deposits underneath Sitka Sound. Pyroclastic flows are the ground-hugging avalanches of hot gas and ash that run down a volcano's flanks at high speed. Finding their deposits beneath the Sound means that during that phase, the flows reach the water. The water they reached is the water Sitka sits on. After that, the field quieted down considerably. There were smaller eruptions in the range of 6,000 to 4,000 years ago. The most recent one that has been well dated from marine ash layers falls between about 4,260 and 4,820 calendar years ago. That would put the last eruption somewhere in the neighborhood of 45 centuries in the past, which is why the volcano is usually described as long dormant. Except that there is another line in the record, and it says something different. Tlingit oral history, recorded from elders including Herman Kitka of Sitka, describes Luke Shah as a mountain that blinked and spouted fire and smoke. The time frame usually attached to that account is around 800 to 900 years ago. The Alaska Volcano Observatory carries this in its own summary of the volcano's history, noting that the geologic record shows quiet for roughly 4,000 years, while the oral tradition reports activity far more recently, perhaps a small fire fountaining event, and stating plainly that the timing of the oral account is uncertain. So there is a gap of about 3,000 years between two sources about the same mountain, and both of them are on the record, and neither has been resolved. It is worth remembering, when weighing that, what happened with the other case in this region, where oral history and geology were tested against each other. The Huna Tlingit account of the glacier advancing on their villages in the 1750s was checked against moraines and buried forests, and the geology confirmed it. The oral record on this coast has a track record. That does not settle the Edgecumbe question. What it does is make the question worth taking seriously, and it puts a specific, testable problem on the table. Is there a young eruptive deposit on Kruzof Island that nobody has dated yet? Which brings this to 2022, and to the single most revealing thing in this entire investigation, though far from the largest. On the 11th of April, 2022, a swarm of small earthquakes started under Mount Edgecumbe. Sitka felt some of it. That got attention, because a long dormant volcano producing a swarm is the kind of thing that requires an answer. The problem was that there were no instruments on the volcano. Alaska has one of the best volcano monitoring programs anywhere, and it is stretched across more than 50 historically active volcanoes, most of them in the Aleutians and along the Alaska Peninsula, where they sit under international air routes. Edgecumbe had been quiet for thousands of years. It had no seismic station of its own, no ground deformation station, nothing dedicated. So researchers went to the archive instead. Satellites carrying imaging radar have been flying over southeast Alaska for years, collecting data continuously, whether or not anybody has a reason to look at it. Radar has a specific virtue here. It works through cloud, which in a place with 230 rainy days a year is the difference between a usable record and no record at all. By comparing the phase of radar returns from repeated passes, you can measure changes in the distance between the satellite and the ground, down to centimeters. A team from the Alaska Volcano Observatory and the Alaska Satellite Facility took 7.5 years of that archived data from 2014 to 2022 and processed it with a prototype system built for exactly this purpose. The ground around Mount Edgecumbe had been rising since August of 2018, not for a few weeks before the earthquake swarm, for 3.5 years before it, at rates up to about 7 centimeters a year along the satellite's line of sight, which by early 2022 added up to something over 10 inches of total uplift. The deforming area is roughly 10.5 miles across, centered about 1.5 miles east of the summit. Reanalysis of a seismic station 25 kilometers away showed small earthquake counts creeping up from about July of 2019, once anyone thought to go looking. Modeling of the deformation pattern points to magma moving between reservoirs, a body at around 20 kilometers depth losing volume, while a shallower one at around 10 kilometers gains it. In plainer terms, magma rising from roughly 12 miles down to roughly 6. The lead author described it as the fastest volcanic deformation currently measured anywhere in Alaska. He also said, in the same coverage, that an eruption is not imminent, that the process had been running for years without one, and that additional signs would be expected first. Both of those statements are important, and they belong together. Since then, the situation has settled somewhat. The uplift rates have declined. No unusual gas emissions or surface changes have been observed. The Alaska Volcano Observatory has kept the alert level at green, meaning normal background. And in August of 2024, the observatory installed a permanent monitoring network on Kruzof Island. 4 stations, combining seismometers and precision satellite positioning. 4 stations, installed in 2024 on a volcano 15 miles from a town after it had already been inflating for 6 years. That sequence is the point of this whole cluster, and it generalizes. The magma did not hide. It moved a mountain's worth of ground upward by 10 inches over an area 10 miles wide, and it did that in the open, in daylight, in view of a town, for 3.5 years. It was not detected because nothing was pointed at it. The only reason it was detected at all is that a different machine, built for other purposes, happened to be recording the whole time, and somebody eventually went back through the tape. That is a very different kind of hidden from the one the phrase usually implies. It is not concealment. It is absence of measurement. And once you have that idea in hand, It starts explaining a great deal about this coast. The 1899 uplift was measured because barnacles kept the record. The 1958 wave height was measured because trees kept the record. The 40,000-year animal sequence survived because limestone kept the record. The Edgecombe inflation was measured because a satellite kept the record without being asked. Almost nothing here has been observed on purpose, in advance, by someone whose job it was, which raises the next question in the sequence, and it is a human one. Who has been here, watching this coast, and what were they actually watching for? Two things need saying about Edgecombe before moving on. One cautionary and one hopeful, and they pull in opposite directions. The cautionary one first, and it has to be stated carefully, because volcano stories attract exaggeration, and this one does not need any. Magma intrudes into the crust far more often than it reaches the surface. Most intrusions stall, cool, and crystallize underground without ever producing an eruption. A body of magma moving from 12 miles down to 6 miles down is a real event, and it is not, by itself, a countdown. The observatory's assessment is that no eruption is imminent. The alert level is normal, the inflation has slowed, and there are no unusual gases or surface changes. Everything published on this points the same way. What the record does establish is what the field is capable of, which is a different statement and a more useful one. The Edgecombe volcanic field, in its big phase at the end of the last glaciation, put down ash a meter deep near where Sitka now stands, and more than 30 meters deep in places on Kruzof Island. It sent pyroclastic flows into the water of Sitka Sound. Its ash has been identified 200 kilometers away. That is what this system did when it was fully awake. And Sitka, today, is a town of about 8,400 people, 15 miles away, on an island, with no road to anywhere, an airport that weather closes, and ferry service that has been running at reduced capacity. In any scenario involving that volcano, the response would depend on boats and aircraft in a place where both are conditional on the weather. Nobody is predicting that scenario. It is simply what the geography would require if it ever happened, and it is worth having thought about once. Now the hopeful part. The technique that caught the Edgecombe inflation, processing long archives of satellite radar automatically to look for ground movement, worked so well on a volcano nobody was watching that it is being scaled up. The prototype developed in Alaska is being expanded to cover volcanoes across the United States. That is a genuinely good outcome, and it comes from the specific structure of the problem. You cannot put 4 monitoring stations on every dormant volcano in the country. You can, however, take radar data that is already being collected for other reasons, run it through a system that flags anything moving, and let the flag tell you where to send the stations. A volcano in southeast Alaska that had been quiet for thousands of years, and that almost nobody outside the region knew was a volcano at all, changed how the country watches all the others. That is the useful shape of this whole subject. The Panhandle keeps producing evidence that turns out to matter well beyond itself, and it keeps producing it by accident, in records that were kept for other purposes, found later by somebody who thought to look. Sitka is the largest city in the United States by area. 4,811 square miles, most of it water and mountain, with about 8,400 people in it. It is a municipal boundary drawn around an island and its surroundings, and it is a good illustration of how administrative lines behave in this region. They are enormous, they are mostly empty of roads, and they were drawn by people whose priorities had very little to do with the ground. The oldest of those lines came from a fur company. In 1799, Alexander Baranov, running the Russian-American company, established a post on the north end of Baranov Island and called it Redoubt St. Michael. The Russians were after sea otter pelts, which at the time were among the most valuable commodities on Earth in the China trade, and the outer coast of southeast Alaska had them in quantity. The post lasted 3 years. In June of 1802, Tlingit forces under leaders remembered as Scout-Lelt and Kotlian destroyed it. The garrison at the time was around 30 Russians, a handful of British deserters, and roughly 200 Alutiiq and Aleut workers brought from further west. The settlement was burned, the pelts taken, and a ship under construction destroyed. Survivors were later ransomed through a British merchant vessel. The reasons are documented, and they are not mysterious. The Russians had taken Tlingit women without compensation, demanded allegiance to a distant emperor, and pressed people into labor. Meanwhile, American traders, the Boston men, were working the same coast, paying substantially better for furs and selling the Tlingit muskets, powder, and at least one small cannon. The Tlingit had both the motive and the means, and they used them. 2 years later, Baranov came back with a fleet. The Russian force in the autumn of 1804 included over 150 Russian Promyshleniks, 400 to 500 Alutiiq and Aleut hunters in something like 250 skin boats, and the naval sloop Neva under Lieutenant Yuri Lisiansky, carrying 14 guns. The Kiksdat-Adi clan, whose territory this was, had prepared. They had built a fort at the mouth of Indian River, called Shiski Nu, roughly 240 feet by 165, made of something like 1,000 spruce logs, with 14 dwellings inside. The siting was deliberate, and it was tactical. They put it on shallow tide flats, where a ship of the Neva's draft could not get close enough to bring its guns properly to bear. The Tlingit war leader was Kalyan, usually written as Katlian, who fought wearing a raven crest helmet. The Russian landing party was thrown back. Baranov himself was shot in the chest and pulled to the water's edge, and what saved the landing force from destruction was covering fire from the ship. The battle ran across the first days of October. What broke it, according to Tlingit accounts, was an accident. A canoe bringing gunpowder to the fort was struck, and the powder went up, killing a group of young men from leading families and several elders. Without the powder, the fort could not be held. On the evening of the 4th of October, the Kiksdat-Adi left on their own terms. They walked out overland, through the mountains of Baranof Island, in what is remembered as the Kiks-Adi Survival March, north to Point Craven and then by canoe across to Chichagof Island. It took days in October in that country with children and elders. The Russians founded New Archangel on the site. By 1808, it was the capital of Russian America, and it stayed the administrative center of the Russian presence until 1867, which is when the map problem starts. The Russians never controlled southeast Alaska in any meaningful sense. They held a fortified town, a few posts, and a trade network. When the United States purchased Alaska in 1867, what it purchased in this region was whatever Russia's claim had been, and Russia's claim rested on a treaty signed with Britain in 1825 by negotiators in Europe, describing terrain that none of them had seen. The relevant sentence in that treaty is one of the more consequential pieces of vague writing in North American history. The boundary was to run up the Portland Channel to the 56th parallel, and from there follow the crest of the mountains that run parallel to the coast. And in the event those mountains should turn out to lie more than 10 marine leagues from the ocean, the boundary would instead follow a line parallel to the sinuosities of the coast, never more than 10 marine leagues from it. 10 marine leagues is about 35 miles. The strip that definition creates is called the lisière, the French word for a selvage, the finished edge of a piece of cloth. The mainland ribbon of the Alaska Panhandle is that edge. The problem is the phrase parallel to the sinuosities of the coast. Which coast? The United States said it meant the actual shoreline, including the full length of every fjord, measured from the heads of the inlets. Under that reading, the strip stays continuous, and every inlet on the Panhandle, all the way to its innermost end, is American. Canada said it meant the general trend of the coast, measured from a line drawn across the mouths of the inlets. Under that reading, the 35 miles gets measured from further out, The inlets punch through the strip, and Canada reaches salt water at the heads of several fjords, including Lynn Canal. For 70 years, this was an academic dispute about a rainforest almost nobody in either capital cared about. Then, in 1896, gold was found on a tributary of the Klondike River, in the Yukon. What followed put something like 100,000 people in motion toward a place most of them could not find on a map. Dawson City went from a few hundred people to roughly 17,000 within 2 years. And the practical route to the Klondike ran through two beach towns at the head of Lynn Canal, at the northern tip of the Panhandle, Skagway and Daya, the trailheads for the White Pass and the Chilkoot Pass. Skagway went from essentially nothing to somewhere between 8 and 10,000 people by the summer of 1898, briefly the largest town in Alaska. Suddenly, the question of who owned the head of Lynn Canal was worth a great deal of money and a great deal of national pride. Canada wanted an all-Canadian route to its own goldfields and had no port on that coast. Negotiations collapsed in February of 1899. In October, the two sides agreed to a provisional line as a temporary measure, drawn to leave Skagway and Daya under American control while the argument continued. In January of 1903, Secretary of State John Hay and the British ambassador Michael Herbert signed a treaty submitting the whole thing to arbitration. The tribunal had 6 members, 3 appointed by the United States, 2 by Canada, 1 by Britain. The treaty specified impartial jurists of repute. The United States appointed Elihu Root, who was the sitting Secretary of War, Henry Cabot Lodge, a sitting senator who had already stated his views on the case in public, and George Turner, a former senator. Canada appointed Sir Louis Amable Jeté, the Lieutenant Governor of Quebec, and Allen Aylesworth, a Toronto lawyer. Britain appointed Lord Alverston, the Lord Chief Justice of England. Canadians pointed out immediately that the American appointments were politicians when the treaty had specified jurists, and that one of them had publicly prejudged the case. They were right about the facts. It did not change the composition of the tribunal. The award came on the 20th of October, 1903. The vote was 4-2. Alverston sided with the 3 Americans. Lynn Canal stayed American in its entirety. Canada got no port on the Panhandle. The line ran, as the Americans had argued, around the heads of the inlets, keeping the strip unbroken from top to bottom. At the southern end, where Portland Canal comes in, the tribunal split the difference in a way that has been argued about ever since. It defined the Portland Channel of the 1825 treaty as passing north of Pierce Island and Wales Island, and then out to sea through Tongass Passage. That put Pierce and Wales on the Canadian side and 2 smaller islands, Sitklin and Canaghoonut, on the American side. Canada had claimed all 4. A salmon cannery built on Wales Island in 1902, on the assumption that it was American, was now in British Columbia. The 2 Canadian members refused to sign the award. The reaction in Canada was severe, and it lasted. The decision was read, not unreasonably, as Britain trading Canadian territory for good relations with Washington. Wilfrid Laurier told the House of Commons that so long as Canada remained a dependency of the British Crown, the powers Canada held were not sufficient to maintain its own rights. The line from that grievance to the creation of a Canadian Department of External Affairs in 1909, and eventually to full Canadian control of its own foreign policy, is direct and is drawn by historians routinely. An argument about the width of a strip of rainforest helped push a country toward independence. The line itself is still there, and it is maintained, and it is one of the odder physical objects in North America. The Alaska portion of the Canada-United States boundary runs about 1,538 miles, of which roughly 1,357 miles are over land. Along the entire land boundary, an international commission keeps a cleared strip of forest 20 feet wide, 10 feet on each side of the line. cut and maintained so the boundary remains visible to the skyline. Boundary-wide, that commission looks after more than 8,000 monuments and reference points. On the northern segment, along the 141st meridian, survey crews had by 1913 planted 202 obelisks running from the Arctic Ocean south to a glacier. There is a mowed line through the temperate rainforest of southeast Alaska, South Alaska kept clear for over a century because of a sentence about mountains written in 1825 by people who had never seen them, and a vote taken in a room in London in 1903. One thing about all of this needs saying plainly. Every party to that argument was a colonial government. The Tlingit, the Haida, and the Tsimshian, whose territories the line crosses and whose clans have relatives on both sides of it, were not parties to the 1825 treaty, the 1867 purchase, or the 1903 arbitration. The boundary was drawn across their country by people negotiating about their country without them. The legal response to that came from the communities themselves. In 1935, Congress passed an act allowing the Tlingit and Haida to bring suit against the United States over lands taken from them. To do that, they needed a single body that could act for them all, and the Central Council of the Tlingit and Haida Indian Tribes of Alaska was organized for that purpose at the end of the 1930s, growing out of the Alaska Native Brotherhood. It is a federally recognized tribal government today, headquartered in Juneau, with more than 38,000 tribal citizens. That is the human overlay in its oldest form. There are two newer layers on top of it, and both of them are about what people came here to take out of the ground. There is one community in the Panhandle that exists because people decided the boundary was useful. In 1887, more than a decade before the arbitration, and while the line was still an unresolved argument between two governments, several hundred Tsimshian left the mission village of Metlakatla in British Columbia. They were led by William Duncan, a lay missionary who had fallen out badly with the Anglican Church hierarchy and with the colonial administration over questions of authority and land. They loaded canoes and moved north across the disputed line, onto Annette Island in what was then American territory. They built a new town, kept the old name, and in 1891, Congress formally set the island aside as a reserve for them. That reserve is still there. Metlakatla on Annette Island is the only federal Indian reservation in the state of Alaska. When the Alaska Native Claims Settlement Act reorganized native landholding across the entire state in 1971, converting traditional territory into shares in regional and village corporations, Metlakatla was the one native community that declined to participate. It kept the reserve instead. The result is that the southern end of the Alaska Panhandle contains a Tsimshian community of about 1,500 people whose land is held under an entirely different legal regime than every other native community in Alaska, because of a decision made in 1887 by people who looked at an unsettled international boundary and worked out which side of it they wanted to be on. When people describe the Tongass by its extent, they usually say it runs from Metlakatla in the south to Yakutat in the north, about 450 miles. Both of those anchor points are native communities. The forest is described in official language by the Rimskakwakan's Batishore, by the distance between them. That is a reasonable place to correct a misconception that the framing of this whole subject invites. The people who live in the Alaska Panhandle know it intensively, in ways that have never resembled a survey report. Fishermen know where the water does strange things. Hunters know which slopes slide. Families know which beaches are safe to camp on at which stage of the tide. Clan histories carry accounts of glaciers, waves, and eruptions across centuries. In several documented cases in this region, that knowledge has turned out to be right in advance of the instruments. What almost nobody has, resident or otherwise, is the assembled version. The fault maps, the tide gauge series, the radar interferograms, The cave inventories, the ash cores, the rainfall thresholds, and the survey notebooks live in different institutions, in different formats, written for different audiences, and they are almost never read against each other. That is the sense in which something here is hidden. It is scattered across archives in plain sight, waiting for somebody to put it in one place. On the 18th of May, 1955, a small aircraft was flying a radiation survey over the southern end of Prince of Wales Island. The men aboard belonged to an outfit that had been in existence for about a month. 3 of them, Don Ross, Kelly Adams, and Bill Easton, had pooled roughly $6,000 in April and called themselves the Uranium-55 Syndicate. This was the height of the uranium boom, when the Atomic Energy Commission was guaranteeing to buy ore and prospectors were flying Geiger counters over anything that looked promising. Over a peak called Bocan Mountain, the counter went off the scale. They landed at a lake about 2 miles away, walked in, and staked the claim the next day. Accounts differ about which man was in the air and which was on the ground, and the 2 best sources contradict each other on that detail, which is a good reminder that a founding story gets tidied up in retelling. What is solid is the date and the 3 names. A mining trade magazine named it the United States Discovery of the Year. The Ross Adams mine operated at the head of Kendrick Bay, on and off, from the late 1950s until 1971, in 3 separate campaigns, on contracts with the Atomic Energy Commission, both open pit and underground. The production figures published by different agencies do not reconcile cleanly, which is common for that era, but the general scale is on the order of 1.3 million pounds of uranium oxide from something like 90,000 tons of unusually high-grade ore. It remains the only uranium mine that has ever produced in Alaska. There was no mill on site. Ore went out by ship for processing elsewhere, which is why the site does not carry the tailings problem that defines uranium districts in the American Southwest. It does carry something. A preliminary site inspection in 2004 found elevated radiation at the workings, in the waste rock piles and along nearby roads, with radon inside the old underground workings at many times the level permitted for indoor exposure, and ambient readings in the immediate area running above natural background. A larger investigation in 2009 added gamma surveys and sampling of soil, surface water, stream sediment, marine sediment, and air. In August of 2020, the Forest Service signed a settlement agreement with 2 mining companies for a comprehensive cleanup, estimated at around $7 million. And the mountain is back in play for a different element. The same intrusive rock body that concentrated uranium at Bocan also concentrated rare earth elements. A company called Ucore has been drilling the Dotson Ridge zone there since 2008. Its updated resource estimate, published in April of 2026, reports an indicated resource of about 800,000 tons, grading 0.6% total rare earth oxide, and an inferred resource of about 10 million tons at 0.51%. The number that makes people pay attention is a different one. At Bocan, heavy rare earth elements make up something like 35 to 40% of the total rare earth content. Most deposits in the world are dominated by the light end. The heavy end is where the strategically awkward elements sit, the ones used in high-temperature magnets and specialized optics, and the ones whose supply chains are concentrated in very few countries. Bocan remains a property in development, with the company's stated near-term focus on a processing plant elsewhere in the country. Still, the pattern is worth naming. The mountain did not change between 1955 and now. The list of elements the world was anxious about did. Now, the strangest political artifact on this coast, which sits at the very bottom of the Panhandle, where the 1903 line came ashore. Portland Canal is a fjord, about 71 miles long, named by Vancouver in 1793 for a British duke. The word canal is a leftover from Spanish charting conventions. Nobody dug it. The boundary the tribunal fixed runs down the middle of it, which means that for 71 miles, the water on your left is Canadian, and the water on your right is American. At the head of it, on the American side, is Hyder. The population of Hyder was 48 at the 2020 census, down from 87 a decade earlier. It has no road connection to anywhere else in Alaska. It has a road connection to Stewart, British Columbia, which is 2 miles away. So Hyder runs on Canada. The electricity comes from a subsidiary of a British Columbia utility. Both currencies circulate. And the post office is generally the only place in town that takes American dollars exclusively. The telephone numbers use Canadian area codes and Stewart's exchanges. The town is officially on Alaska time, and residents keep British Columbia time, which is an hour different, because the people they interact with daily are in British Columbia. The school operates only when there are at least 10 school-age children in town, and when there are not, the students go to school in Stewart. The border arrangement is the part that always gets me. There is a Canadian border post on the only road out of Hyder. There is no American checkpoint on the American side. Traffic is inspected going into Canada. Coming back into the United States, there is a road. Hyder was founded in 1907 as Portland City and renamed in 1914 after a Canadian mining engineer. It had a real mining boom from the 1920s into the 50s. What is left is a settlement that exists in one country and functions in another, entirely because of where a line was drawn. Around and above all of this sits the forest, and the forest is the largest single thing in the region by a wide margin. The Tongass National Forest covers 16.7 million acres. It is the largest national forest in the United States, and it takes in roughly 80% of the Alaska Panhandle. It was established in 1907 by proclamation. About 10 million acres of it are actually forested. The rest is rock, ice, muskeg, and water. It holds 19 designated wilderness areas totaling more than 5.75 million acres, more wilderness than any other national forest. The best description of it is the largest intact temperate rainforest remaining on Earth. Temperate rainforest is a rare forest type worldwide, and most of it has been logged. This is the biggest piece still standing. The old growth accounting is worth doing carefully because two different numbers get quoted, and they mean different things. Counting all classes of old growth, most of the original extent is still there. But the class that matters most, the low elevation, big tree stands on the productive valley bottoms, was always the smallest and was cut first. Of roughly 491,000 acres of that class originally, about 383,000 remain, around 78%. That is the honest figure, and it is the one to use. About 30 communities sit inside the forest, ranging from settlements of 18 people to Juneau's 30,000, along with 19 federally recognized tribes. The policy history of this place is its own kind of instability. In 2001, the National Roadless Rule was applied to the Tongass, covering something over 9 million acres, more than half the forest. In 2020, the Tongass was exempted from it. In 2023, the exemption was repealed, and the protections restored. In 2025, the administration announced its intent to rescind the roadless rule nationwide. And as of this year, that rescission is a proposed rule sitting in a public comment period, alongside a full revision of the Tongass Land Management Plan that opened in February and is scheduled to produce a final plan in 2027. 4 reversals of basic road policy on the largest national forest in the country inside a quarter century. Whatever anyone thinks about the substance, that is a difficult environment in which to run a sawmill, a tour company, or a tribal forestry program. Then there is the matter of how anyone gets anywhere. The Alaska Marine Highway System is a state ferry network covering about 3,500 miles of route. Hoboken-Mausensekrewer from Bellingham, Washington, all the way out to the Aleutians, serving more than 30 port communities. In 2002, it was designated a National Scenic Byway, which means the United States has an officially designated scenic highway made entirely of salt water. For most of the Panhandle, it is the road. Juneau, Sitka, Ketchikan, Wrangell, Petersburg, Angoon, Hoona, Cake, Metlakatla, Pelican, Tenakee Springs, Craig, Clawawk. None of them connect by road to anywhere outside themselves. Haines and Skagway are the exceptions, at the very top, where highways run up into Canada. Juneau is the only state capital in the country that cannot be reached by road from the rest of its own state. There was a plan to change that. The Juneau Access Project would have run about 50 miles of new highway north along Lynn Canal to the Katsahin River, with a short ferry shuttle from there to Haines and Skagway. It was studied for decades, argued about bitterly, and roughly $40 million was spent on it. In December of 2016, the governor selected the no-build option, citing the state's fiscal situation. In July of 2018, the Federal Highway Administration issued a formal no-build decision and closed the file. Meanwhile, the fleet has aged. The average vessel is in its mid-30s and some are past 60. Earlier this year, the system was running 6 of its 9 vessels. Yakutat has had no ferry service since 2023. One 52-year-old ship is being kept in service until a replacement can be built. The whole system moves something like 350,000 passengers and 100,000 vehicles a year, and there is no alternative for the communities that depend on it. And then there is the weather, which in Juneau has a name. The taku is the wind that comes over the ridges above the capital in winter. The folk explanation, and it is a reasonable one, is that cold, dense air pools over the ice field and drains down to the sea. The careful study of it, published in 1992, found something more specific and more violent. The taku is an amplified mountain wave, a severe downslope windstorm in the same physical family as the windstorms that come off the Front Range in Colorado. Air flows over the barrier, the wave in the flow amplifies, and it slams down the lee side. It needs 3 conditions together: a temperature inversion sitting right about at ridgetop height, strong flow across the barrier at that level, and that flow weakening with height above it. Ordinary gap winds, which are much more common, need only a pressure difference between one side of the mountains and the other. That distinction is why Juneau gets windy often and gets a true taku about 4 times a year between October and April, most often in January or February. During those events, hurricane-force gusts show up roughly every other year. The airport's all-time recorded gust is 92 miles an hour. Downtown sensors have logged 78 and 85 in various events, though the record downtown is acknowledged to be patchy because the instruments have moved around over the years. In one of those winters, the wind moved a 15,000-pound gangway in the boat harbor at Douglas. The airport those winds blow across sites in Gastineau Channel, with ridges over 3,000 feet on both sides and barely a mile of width in places. The instrument approach to one of its runway directions is a satellite-guided procedure flown down the channel with a turn every few miles, ending with the aircraft rolling wings level a few hundred feet above the ground. It is proprietary to one airline, it requires specific crew qualification, and it exists because a conventional straight-in approach into that fjord is not available. That is the practical shape of life here. A capital city you cannot drive to, reached by an approach that requires special training or by a ferry fleet running at 2/3 strength, in a place where the wind has a proper noun and the rain is measured in feet. Now, the question this whole investigation has been building toward: given everything the Panhandle is physically capable of, how much of that capability is actually being watched? Unknown is a lazy word. It gets used for at least 5 different situations that have nothing in common except that somebody does not have an answer, and separating them is the only way to say anything useful about what is actually left here. So let me sort the Panhandle's unknowns into their real categories, because the interesting one only becomes visible once the others are cleared away. Category 1. Genuinely unmapped. Start with the sea floor, which in this region is most of the surface area. The Alaska Panhandle is a drowned mountain range. The channels between the islands are canyons. The fjords are valleys with water in them. And the fault that organizes the whole system spends most of its length underwater. The state of the mapping is not good. Roughly half of Alaska's waters have any published seafloor mapping at all, and published is doing a lot of work in that sentence, because it includes surveys of wildly different vintage and quality. Some of the small-scale charts covering Alaskan waters still incorporate soundings that trace back to Cook's voyages in the 1770s, and in a few areas to Bering, around 1740. A lead line sounding is a rope with a weight dropped over the side. It gives you an accurate depth at one point. It tells you nothing whatsoever about what is between that point and the next one. Modern multi-beam sonar paints a continuous surface. The difference between a chart built from scattered points and a chart built from continuous coverage is the difference between knowing a few depths and knowing the shape of the bottom. That matters for 3 separate reasons here, and they compound. First, ships, narrow fjords, strong tides, and thousands of passenger movements a day in summer over bathymetry that in places rests on very old, very sparse data. Second, the fault. Offshore strands are the parts that produce the largest earthquakes on this system, and mapping their geometry, their bends, and their steps requires seeing the sea floor in detail. The high-resolution work that produced those fast slip rate estimates for the submarine section is relatively recent, and it covers a fraction of the length. Third, waves. What a landslide-generated wave does after it leaves the slope depends on the shape of the basin it enters. Modeling the hazard in a fjord requires knowing the fjord's floor. Where the bathymetry is coarse, the model is coarse. The unmapped category extends inland too. More than 600 caves are known on Prince of Wales Island, and the reason we know that many is that a systematic survey effort only really began in the 1990s. There is no basis at all for believing the inventory is finished. Every serious expedition into that karst has found more passage. The number is a floor, and the landslide record has the same shape. 12 to 15,000 slides are mapped across the Tongass, from decades of aerial photography and fieldwork. It is a good inventory of scars. It says very little about when they happened or what they hit, which is why, in 2024, researchers had to build the database of landslide impacts on Southeast Alaska communities by going through 34 years of local newspapers. Category 2. Hidden from view in the plainest possible sense. This coast is under cloud most of the time. Juneau has roughly 230 days a year with measurable precipitation. Overcast is the default state. And under the cloud, over most of the land surface, there is a closed forest canopy of spruce and hemlock. Optical satellites and ordinary aerial photography are close to useless for large parts of the year, and where they do work, they see treetops. Determining the actual shape of the ground beneath a temperate rainforest requires laser scanning from aircraft, which works but is expensive and has to be flown in weather windows that this region does not hand out generously. This is precisely why the Mount Edgecumbe discovery came from radar. Radar does not care about cloud. It was the one instrument that could see, and it was seeing on autopilot, for a purpose that had nothing to do with that volcano. Category 3. Restricted. There is remarkably little of this, and what exists is almost entirely protective. The place where Shuka Ka was reburied in 2008 has not been published. That is a decision made by the communities whose ancestor he is, and it belongs in the category of privacy. Cave locations across the karst are routinely withheld by land managers, which is standard practice worldwide for caves that contain fragile formations or archaeological deposits, because publishing a coordinate is the fastest way to destroy a site. Certain waters in Glacier Bay close seasonally to vessels while seals are pupping. Add up everything genuinely closed off in the Alaska Panhandle and you get graves, caves, and seals. There is no locked door here concealing anything important about the geology. Category 4, poorly sampled. This is the big one, and it is where most of the real uncertainty lives. Sitka has been studied harder than anywhere else in the region for landslide hazard with federal researchers, university teams, and a dedicated warning system. The sample underneath all of that is 5 landslide-triggering rainfall events across 18 years. 136 statistical models were run against a dataset with 5 positive cases in it. The researchers said so themselves, in the paper plainly, and then explained why they proceeded anyway, which is that 5 is what exists, and a town needed a threshold. Mount Edgecombe had no dedicated instrument until August of 2024. Everything known about the 2018 to 2022 episode was reconstructed after the fact from data collected for other reasons. The earthquake record is thinner than it looks. Instrumental seismology in southeast Alaska covers a few decades. The written record covers a bit over 2 centuries. The fault produces great earthquakes on any given segment on a timescale that may run to several centuries. A 200-year record sampling a 500-year process will show you some of it and mislead you about the rest. And the work being done now on offset landforms and buried soils is precisely an attempt to reach further back than the writing does. Permanent positioning stations measuring uplift are excellent where they exist and are sparse across most of the region. Tide gauges likewise. The measurement is concentrated where the people are, which is reasonable and also means the empty 90% is largely uninstrumented. Category 5. Scientifically unresolved. These are the questions where more data would help, but the disagreement is real and current. Whether ice-free ground persisted in the Alexander Archipelago through the last glacial maximum. Bare bones from the caves say animals were living here. Cosmogenic exposure dating on bedrock says the surfaces were covered. Both bodies of evidence are solid, and they point opposite directions. When Mount Edgecombe last erupted. The dated ash record says something over 4,000 years ago. Tlingit oral history says 8 or 900. That is a 3,000-year discrepancy about a mountain in plain sight of a town, and it has not been closed. Whether large slope failures into fjords are becoming more frequent as the tidewater glaciers withdraw. The mechanism is well understood, and the physical reasoning is straightforward. The rate is another matter because the record of such events is very short, and before satellite radar and dense seismic networks, most of them happened in places where nobody was present to notice. And the largest one, how big the Queen Charlotte and Fairweather system can go. 1949 ruptured more than 300 miles. Whether the system can link segments into something longer, and how long the intervals are on the segments that have not moved in living memory, is not settled. Now step back and notice what all 5 categories have in common. Not one of them is about concealment. Not one of them involves a person deciding that the public should not know something. The Panhandle's unknowns are functions of area, terrain, weather, cost, and the shortness of the written record. The region is huge, mostly vertical, mostly wet, mostly forested, mostly underwater at the edges, and it has had instruments on it for a few decades at most, which produces a clean 2-part statement about this place, and I think it is the most accurate summary available. What the Alaska Panhandle is physically capable of is well established. Fault slip rates, uplift rates, run-up heights, ash volumes, rainfall thresholds, retreat distances, all measured, all published, all repeatable. What the Alaska Panhandle is doing right now across most of its surface is largely unobserved. That gap between capability and observation is the actual answer to the question this started with. It is why a mountainside can fail into a fjord full of tour boats and be recorded, in effect, by a tide gauge 80 miles away. It is why a volcano can inflate for 3.5 years in daylight. It is why the deadliest landslide in the region's recent history came out of a 1-year storm. But that is a statement about instruments. It is not the deepest thing still open here, and it is not where I want to leave this. There is one question about this coast that is unresolved in a different way. It is not a matter of putting more sensors out. The evidence needed to answer it is physically displaced systematically by the very processes this whole investigation has been tracking. And until somebody works out where it went, the question stays open. It concerns the people who were here first. Anywhere else on Earth, looking for the oldest coastal archaeology is a fairly clean proposition. During the last glacial maximum, a great deal of the planet's water was locked up in ice sheets, so global sea level stood roughly 400 feet lower than it does now. The beaches people used are therefore offshore and underwater, at a depth you can estimate from a global curve. And marine archaeologists go and look there. That approach does not work in Southeast Alaska, and the reason it does not work is every single mechanism this investigation has been tracking, operating at once. Sea level is a relationship between two things, where the water is and where the land is. The global curve only describes the water. Along this coast, the land has been the more energetic partner. Here is what the crust actually did. An ice sheet is heavy. Put one on the crust, and the crust sinks, and the mantle beneath it, behaving over long time scales, like a very stiff fluid, squeezes out sideways. That displaced material has to go somewhere. It goes just beyond the edge of the ice, and it pushes the crust there upward. Geologists call that a peripheral forebulge. Picture setting a heavy weight on a mattress. The mattress goes down under the weight and rises in a ring around it. Southeast Alaska sat across both parts of that pattern. The mainland side, under the thick ice of the coast mountains, went down. The outer islands of the Alexander Archipelago sat out on the bulge and went up. Then the ice left, and the whole arrangement reversed. The depressed interior began rising, which it is still doing today, at up to about 1.1 inches a year in Upper Glacier Bay, and the forebulge collapsed, which meant the outer islands went down relative to the water. The measured consequences are startling. In parts of the Alexander Archipelago, relative sea level fell roughly 50 meters, about 165 feet, as the forebulge subsided between about 15,000 and 10,000 years ago. In the southern part of the region, ancient shorelines have been mapped as much as 25 meters, some 80 feet, above the present-day sea, marking the high point of a rise that peaked around 11,000 to 10,500 years ago. And along the same general coastline, other stretches went in the opposite direction on a different schedule. Add it up, and you get the thing that makes this problem genuinely hard. There is no single elevation for the shoreline of 12,000 years ago in Southeast Alaska. There is a family of curves, one for each stretch of coast, and adjacent stretches can differ by hundreds of vertical feet in opposite directions, over distances of tens of miles. A beach that a person walked on 11,000 years ago might now be 80 feet up a forested hillside, buried under a century of moss and root mass and blowdown, under a canopy that hides the ground from every airborne camera. Or it might be 150 feet down, on a fjord floor whose bathymetry has never been surveyed at anything better than a scattering of individual soundings, some of which date to the age of sail. And the same tectonic activity that makes this coast interesting has been continuously rearranging the evidence in the meantime. Earthquakes lift and drop sections of shoreline by tens of feet in an afternoon. Landslides bury beaches. Glaciers advance and scrape valleys back to rock, then withdraw and leave the ground rising for centuries afterward. Now put the pieces together, because the question this leaves is very specific. We know that a man lived on the outer coast of what is now Prince of Wales Island around 10,300 years ago. We know from his own bone chemistry that he ate almost nothing but food from the sea. We know he was carrying tools made from volcanic glass that came from hundreds of miles inland. We know from his genome that his relatives are the Tlingit, Haida, and Tsimshian people who live on this coast today, which is what those communities have said all along. He was not the beginning of anything. A person that thoroughly adapted to a marine life, that well supplied through a trade network, is standing near the middle of a long sequence, and the earlier part of that sequence should be somewhere on this coast. What nobody can currently say is where to stand to find it. That is the exact unresolved boundary. Not whether people came down this coast early, not whether the archipelago could support them. The open question is a matter of coordinates. For any given stretch of this shoreline, at what elevation was the waterline 11, 13, 15,000 years ago, and therefore, where do you put the survey? Answering that requires reconstructing the relative sea level history, stretch by stretch, using dated shells, dated marine sediments, raised beach deposits and drowned features, and then searching the reconstructed shorelines. Where that has been done, it has worked. Surveys guided by sea level reconstruction have located sites that random searching would never have found. The method is sound. It has simply never been carried out at the scale of a 500-mile coastline with 1,100 islands in front of it. Until it is, the oldest confirmed human evidence in Southeast Alaska will remain what it has been since 1996. A handful of bone fragments from a cave floor, 10,300 years old, belonging to a man whose descendants named him Shuka Ka, man ahead of us. The record on this coast stops there. The coast is not empty, and nobody is keeping it quiet. It stops because the ground that would answer the question has been lifted, drowned, and tilted at a different rate along every mile of this shore, and nobody has finished working out where it went. That is where the case closes, and it closes without an answer, which I think is the honest place for it to end. One thing worth adding, and I mean it as a real question, a great deal of the strongest evidence in this investigation came from people who were paying attention long before anyone brought an instrument out here. A Tlingit account of a glacier advancing faster than a dog could run, later checked against moraines, and buried wood and confirmed. An oral record of a mountain spouting fire that the dated ash layers still cannot account for. Thousands of Lingit, Shadkeel, and Samalgiaks place names along this coast, a great many of which describe precisely what the water or the ground does in that exact spot, which is the oldest form of hazard mapping there is. Local knowledge on this coast has a documented track record of arriving first, so if you have spent time up there, on the ferry, on a fishing boat, on a beach in the rain, tell me what you have seen that nobody wrote down. A slope that lets go every few years. A creek that changed, a place the old-timers will not anchor. That is the sort of thing that turns into a survey line 20 years later. And if you want more of this kind of thing, a like and a subscribe are how it finds the people who would care about it. Leave the observation in the comments. The record on this coast has always been built out of exactly that.